Hidden from the naked eye is a universe we barely understand. There are stars being born, black holes, perhaps even new forms of life. But now astronomers are able to see the cosmos as never before. They are creating a new breed of super telescope of unprecedented power and clarity.
We have at our disposal tools that have never existed before in the history of mankind. We're the first ones to get to look at this. You know, you don't actually realize how special a time this is.
This revolution in telescope construction promises a new age of discovery.
Right now is an extremely exciting time to be an astronomer, to be an engineer building telescopes, because the questions keep multiplying. The answers keep coming too, but the questions come even faster than the answers.
Engine start at 7:15, we'll taxi out at 7:25.
At the ends of the Earth, astronomers are trying to capture light that has traveled from the farthest reaches of space.
We're taking it to the Chaknantor Plateau. The air density is about 50% that of sea level.
Gloves on, hat on, oxygen happening. More or less ready for the Chilean desert.
Together, they are reinventing what a telescope is and what it can do. And they are rewriting the story of the universe. The Atacama Desert, Chile. Hardly any vegetation, moisture, or life. Mountains here have received no rain in living memory. They reach up over 1.5 miles into dry, cloudless skies. Throughout history, only death awaited those who ventured here. Until now. This is La Residencia. But this is no luxury hotel, and the people here are no ordinary tourists. This is the desert home away from home for astronomers hunting for the most mysterious and elusive objects in the universe.
It's very exciting to be out here in the desert, and what we are actually doing here is we are looking for a very particular object in our own galaxy. We're looking for a black hole.
To locate this black hole, astronomers will be using one of the most powerful telescopes ever built. The VLT, the Very Large Telescope. This is the most advanced optical instrument ever constructed. The VLT is made up of 4 main telescopes. Each contains identical glass ceramic mirrors, the largest ever manufactured. This is what it takes to spot a black hole. But it's not going to be easy, even with the VLT. A black hole, the dense remains of a dead star, has such a strong gravitational pull that nothing can escape, even light.
A black hole collects all the light, so from a certain distance from the black hole, no light can escape anymore. So in that sense, you cannot observe a black hole because it's black.
To locate it, astronomers will be searching for clues in infrared light, light which lies just outside the visible part of the spectrum. It is why the VLT is in the Atacama.
You need the most advanced facilities to observe this. And to do so, you need also certain sites that are dry, for example. And so this desert here is just the perfect place for such a research.
Dry air is vital. Atmospheric moisture filters out infrared light coming from space. By building their telescope above the clouds on a desert mountaintop, astronomers hope for the clearest possible view. It is now late afternoon. Inside the 4 telescopes, engineers are preparing for the coming night's observations. These 23-ton mirrors are fully automated and will be programmed in advance. This 530-square-foot surface can observe objects 4 billion times fainter than can be seen with the naked eye, ideal for finding a distant black hole. As the engineering shift ends, the black hole hunter's shift begins. Gunther and his colleague Andreas will be working through to dawn. To find the black hole, they need still clear, dry skies. And this appears to be the perfect spot. These are the clearest skies on Earth. Back in the control room, the black hole hunters are still hard at work. Theirs is a world fueled by strong coffee.
To be here at 4:30 local time in the morning is very exciting because this is what it is about to be an astronomer. We're sitting here and looking at this phenomenon we are interested in. And of course, you have to go home to analyze your data and to interpret the data and to try to understand what is going on. But beyond that, you simply see the phenomena, and that is, what all the excitement is about.
It might look like any other office, but here they are closing in on one of the most powerful and elusive objects in space.
So here we have an image of the central region of the galaxy, and it's actually taken in the infrared. Its size is about 300 by 100 light years. The stellar density is highest here. This is where the heart of the Milky Way is located. That's what we're interested in, and we can now zoom into this region. And this is actually a slice taken at the center of the galaxy. Over here, you see a small cluster of high-velocity stars. They are orbiting this spot here.
These orbiting stars emit vast quantities of gas, and it's the behavior of this gas that holds the key to the location of the black hole.
If we have a massive black hole and gas coming towards it, it's going to be accreted around the black hole and may form a so-called accretion disk. So this is then hot gas orbiting the massive black hole. So the light coming from that region tells to us astronomers that this actually here at the center of the Milky Way, this object is the location of a massive black hole.
It's a clever piece of detective work. This insignificant-looking dot pinpoints the supermassive black hole at the very heart of our own galaxy. It might not look like much, but these few pixels in reality cover an area about 27 million miles across. The black hole they orbit is thought to be 4 million times heavier than our own sun.
Studying black holes and doing astrophysics brings you basically to the limits of understanding. It brings you to the limits of how we can describe the world that we're living in. So in the process of understanding our world, telescopes are very important because they basically represent the eyes with which we look at the universe.
Scientists Gunther and Andreas end their shift, having just seen the black hole at the center of our galaxy. Just over a decade ago, such observations would have been impossible, as telescopes like the VLT simply didn't exist. At 8,600 feet on top of this desert mountain, the VLT can capture vast amounts of infrared light from space. But not all of it. The atmosphere filters out the rest, even up here in this dry air. To capture this missing light, astronomers have to get their telescopes higher than this mountaintop. Much higher. Palmdale, California. If it's altitude you're after, there are a few better places to come than here.
Play 58, another 10-hour jaunt northwestern United States tonight.
It's the beginning of a long night for astronomer Professor Terry Herder.
Engine start at 7:15. We'll taxi out at 7:25, and takeoff is planned at 7:45, and we'll land at approximately 6 a.m. Aircraft status.
It's good. It's fueled. We do have that the crew oxygen issue, but it's been checked.
Tonight, Terry and his team will be trying to look inside distant nebulae, the cosmic dust clouds where stars are born and die.
Okay, so we're going to start off with an old friend. We've already observed this on a couple of other flights. This is Frosty Leo. This is a nebula in constellation Leo. It's known as a Frosty Leo because it's got ice lines at 43 and 63 microns.
To see these mysterious places, the team will be hunting for infrared light. Unlike visible light, infrared can escape the dust that shrouds a nebula. But to capture this light requires a most unusual telescope. Meet Sofia. Suffice to say, this is no ordinary jumbo jet. This plane has been given a $1 billion makeover. What began as a conventional airliner is now the world's largest mobile astronomical observatory with an infrared telescope beneath the bulge.
That's all I've got. Let's go. Thank you.
It's now late afternoon. This is only the third major research flight for the team. This is the first ever mission to be filmed for television.
Airborne observing is rather unique. It's hard to explain quite how different it is to an astronomer who's never been in this seat. You don't want to waste any time. We're in the air burning fuel. You want to be as efficient as you can. It's sort of funny. I don't get to worry about what goes right usually. I'm worried about what's going wrong and how can I fix it.
NASA 747, copy taxi, we'll hold short of 22 at 0.
By 7 p.m., Sofia is ready for takeoff. For the next 11 hours, the team will be flying an arc-shaped course as their celestial targets move across the sky with the Earth's rotation.
3, 2, 1. Here we go.
NASA 747 Heavy, contact Los Angeles Center 127.1. You have good flight.
This mission is taking Sofia far higher than jumbo jets usually fly.
NASA 747 LA Center, roger. I'll maintain 15,000.
Sofia and her 17-ton telescope is heading for the stratosphere.
November 704, Mike Foxtrot, contact LA Center 132.6.
Here, nearly 8 miles above the planet, she will be above 99% of the water and gases in the atmosphere. At this altitude, the star hunters can make infrared observations which are impossible for ground-based telescopes.
This is, what should I say? This is eye candy for scientists that we're dealing with here.
Tonight, the airborne research team are searching for infrared light, telling the story of the origin and destiny of stars.
We're actually looking at the case where a star is dying and throwing out stuff away from it. And so we're looking at what's called an outflow, or the dying stages of the star.
It's crucial research. The way stars die will influence those born in their place.
The dots we're seeing on the screen right now is a star which is dying. Okay, the name of it is Frosty Leo. It's called Frosty Leo because there's actually water ice associated with it, so frosty.
The specific nature of this research is what makes Sofia's capabilities so important.
Detecting water out among the stars is actually not as easy as you might think. It's very abundant. Because our atmosphere has so much water in it, it's hard to actually observe. So that's why we're in an airplane above this, so we can detect some of those types of objects.
But the technical challenges don't end here. Observing dying stars thousands of years away from the back of a moving airplane is easier said than done. It requires the most sophisticated engineering.
telescope is actually quite amazing in the sense that we are flying in an airplane which moves through the atmosphere, which shakes up and down and moves around. But it can track on the sky and point to an object and keep it fixed there with tremendous accuracy.
Once logged into a celestial target, the telescope stays steady. This isn't the telescope moving inside the plane, but the plane moving around the telescope. Navigating this flying telescope is a unique challenge.
So we're going to go this way until we get to San Antonio, Texas.
As the Earth rotates, the apparent position of their celestial target constantly changes. They have to ensure Sofia is always in the right spot.
People ask me, where are you guys flying tonight? And I say, I don't know, the United States, pretty much.
Right now, to let you know exactly where the airplane is, we are at 41,000 feet. We are flying at 0.85 Mach, or about 550 miles an hour. And right now we're just over Jackson Hole, Wyoming, and we're heading on a southeasterly heading along a desired track to keep the celestial body of interest in the field of view of the telescope.
It's now 4 o'clock in the morning. Back in economy class, the astronomers have observed a stellar nursery in the direction of the constellation Cassiopeia.
What we're looking at here is a region where new stars are being born. This region is a little over, probably about 2,000 light years from us in distance, so we're looking at it back about the time of the Romans. That's when the light originated from here. And what we see here, not only the stars themselves, but there's gas and dust left over from the birth of the stars.
This dust provides a crucial clue to how new stars might form.
The important part about this is basically that the stars themselves, when they're born, affect their environment, which in turn affects the next generation of stars. And so this may help to create other stars in the area being born, or it may actually help them keep them from being formed.
747 Heavy will be a full stop. That's affirmative for 747 Heavy. That's great.
Observing a distant nebula during a bumpy night flight in the back of a jumbo jet is a remarkable achievement.
Flight 208, descend to maintain 900,000.
Sofia doesn't have the magnification power of the VLT, yet her ability to reach the stratosphere means that she can capture certain infrared wavelengths that never make it to the ground.
Heavy, have a good day. Contact Palmdale Tower. Have a good day. Yeah, 747, good day.
But just like the VLT, she will never capture a complete picture. Even at 41,000 feet, infrared light coming from space can't be seen in its full intensity. The latest infrared telescopes are ushering in a golden era in astronomy. These observatories have already started to rewrite the story of the universe. But despite their technical ability, they will only ever contribute a single chapter, not the whole book. To do this requires telescopes that can capture other types of light and examine the clues that this light contains. Back in the Atacama Desert, the quest for different forms of light is driving one of the most ambitious science projects on Earth.
Well, I think there's the potential to get a whole new window on the universe, to actually get away to see into the biggest mysteries and to start to probe the ultimate origins of the universe.
The questions are as big as they come. But the answers lie in the most inaccessible and invisible parts of space.
So some of the biggest mysteries are the cold and dark places in space. If you look right back to as close as we can see to the Big Bang, those are the regions where the first galaxies are forming. But it's very hard to see those regions because of the gas and dust that they're actually forming from.
Very little light can escape these frozen dust clouds. Yet some does make it through. It is known as sub-millimeter radiation. The problem for astronomers is that this form of light has less energy than infrared, making it harder to spot. To stand any chance, they need a radically different style of telescope.
Well, it's very difficult to capture sub-millimeter light because of the technology that's required. We need incredibly sensitive instruments to do it. You need a large telescope because the radiation is very, very weak. And that radiation finds it very, very hard to get through the Earth's atmosphere. And so we go to the highest, driest places on Earth to do that. And it's one of those places that we're going to right now.
At 9,500 feet, on the side of a mountain in the center of the driest desert on Earth, Lewis and his team have built a telescope factory. Here, they are manufacturing large quantities of giant antennas, a necessity for capturing enough of the faint sub-millimeter light. What's so special is the way that all these antennas will be used together. But that won't happen here. They now need to be moved.
So this is, like you might say, a pickup truck, or a Jeep is a 4x4 vehicle. This is a 28 by 28 vehicle.
It's 8 a.m. on a Monday, the start of a busy week.
The science doesn't happen here. Although we've got something like 20 antennas all around us at the moment, this isn't really where the observatory is. The antennas themselves, in order to do astronomy, get taken 25 kilometres from here and nearly 2 kilometres higher up than we are at the moment, which gives us a fantastic view on the universe.
We're taking it to the Chacnantor Plateau, which is very close to the triple border point between Chile, Argentina, and Bolivia. The elevation is about 5,000 meters. The air density is about 50% that of sea level. So we're taking it to a place where there's basically very good astronomical observing conditions.
It will take 3 hours for the transporter to cover the 15 miles up to the 16,500-foot high plateau. For every foot gained in altitude, air density and temperature fall. This is extreme astronomy. Having now ascended 3,600 feet, the team are approaching a danger zone. It's time to check their oxygen levels.
Okay, so we're on the way up to the high side now. We're up at around about 4,000 metres, and because of the altitude, my blood oxygen level will be dropping. So I'm just going to stop and check how that's going. I know it was at about 95% saturation when we started off at the 3,000 metre site. So it's actually pretty good now. It's at about 90. My pulse rate's up a bit, but oxygen level at 90 is very good. We try and always make sure that it stays above 80 as an absolute minimum.
Mistakes made here could be fatal.
It can be very dangerous if your oxygen levels drop too low. The biggest issue for us, for the project, is that your ability to think clearly drops off. People can have acute problems, so certainly people do die of severe altitude sickness.
By midday, the team reached the plateau. It's the perfect location for gathering sub-millimeter light. The antennas here have over 3 miles less air to look through than if they were at sea level. But at this extreme altitude, oxygen is an immediate concern.
So we've arrived at the high site now. We're on the Chacnantor Plateau, an altitude of 5,000 metres. The oxygen levels here are around about half what they are at sea level. So I can feel the difference now. It's pretty cold outside, but I can also feel that my oxygen levels are dropping. Oh. It's freezing up here now. I think the temperature is probably close to 0, and there's a pretty strong westerly wind blowing. So with the wind chill, that takes it well below 0. My oxygen levels have been dropping down in the 70s, which is really not high enough. Open the oxygen bottle, turn the flow rate down. It'll help me to concentrate and help me to think and make me feel a bit better than I do at the moment. So get the cannula in. Well, not the best fashion accessory you've ever seen, but it works.
The whole team is now on oxygen. Without it, operations of this complexity wouldn't be possible. Placing the antenna on the pad is an intricate task, requiring full concentration. Erecting an antenna at 16,500 feet in the Chilean desert requires delicacy and extreme concentration.
Those pads have precision ridges on them. There are 3 ridges. and they'll lower the antenna down onto those ridges, being very careful about the positioning of the antenna. The combination of the skill of the operator and the precision of those ridges means that we can locate this antenna to within around about a millimetre of a known position.
Precision is vital. Each antenna is just a small part of a giant array known as Alma. When it's finished, 66 dishes will operate as one, the equivalent of an antenna 10 miles across. A vast area is needed to capture enough sub-millimeter light. To enhance observations, the array can be reconfigured by relocating individual antennas. The effect will be like a camera zoom lens.
When we have the antennas spaced very close together, that gives us the ability to see large structures in the sky. We can then move those antennas further out onto different pads and make a larger and larger single telescope comprised of those individual antennas. And that gives us the ability to see finer and finer detail.
The complexity and scale of Alma is a measure of the soaring ambitions of 21st century astronomy. Never in human history have we been able to see so far out into the universe with such accuracy.
I think there is something very special about what we get to observe with these sorts of instruments. They don't always produce pictures in the way that we think of the sky, but they produce amazing insights into what's really out there, and they help us understand not only how the universe is created, but they also do really, I think, satisfy our sense of wonder about our place in that universe. I'd really hope that in a few years' time, once Alma's been in operations for a while, that it will have started to reveal the key science that we've built it for. But I also am completely convinced that what Alma will do, like all great observatories, is that it'll detect things that we haven't even predicted that we'll be looking for. It'll be those complete unknowns, I think, that'll revolutionise our understanding of the universe.
But despite the wonder they reveal, even the most advanced telescopes like this can only provide a partial picture of space.
Astronomy now is becoming what we call a panchromatic science, really. You have to combine the information from different wavelengths, from different types of technologies and from different observatories. And that's really where the great advances of astronomy and our understanding of the universe are going to come from.
Now, the very first panchromatic view of the universe is coming together. A breakthrough driven by the 21st century renaissance in telescope construction. This is our nearest galactic neighbor, Centaurus A, seen in visible light. It's a striking image, but an incomplete one. When seen in the infrared, dust clouds begin to emerge. In ultraviolet light, it's clear that these clouds are the nurseries for thousands of bright young stars, all rotating around a central point. But to understand this requires X-ray imaging, which shows high-energy jets coming from the center of the galaxy, the location of a supermassive black hole. But even here, the picture isn't complete. This radio image shows how the jets energize particles deep in space, creating vast radio pulses stretching out over millions of light years. The invisible has been made visible by a combination of telescopes working across the vast spectrum of light. But the quest to understand the universe doesn't end here. It requires a fundamental shift in what telescopes actually look for. The world of telescopes doesn't get much stranger than this. Here in France, astronomers are beginning to redefine what a telescope actually is. Dr. Pascal Coyle is sailing for one of the most unusual telescopes in existence.
We're just now leaving the port of Toulon in the south of France. The telescope is located 40 kilometers offshore.
The Pourquoi Pas is heading for Antares, a telescope designed to spot the most elusive and mysterious cosmic particles of all, the neutrinos.
The neutrinos are a bizarre elementary particle. They have no charge. They essentially have very little mass. So they interact very little with matter. So we have to build telescopes which are enormous to have even the smallest chance to detect just a handful of neutrinos.
Detecting a virtually invisible particle is a real challenge, but if the team's telescope can spot one and work out where it came from, they might rewrite the rules of the universe. Dr. Pascal Coyle is hunting neutrinos with a telescope, not on a mountain, but under the sea.
The boat has now reached the site of the telescope, and it's located 2.5 kilometers below the boat. As you can see, everybody is preparing the submarine to be deployed.
A telescope on the bottom of the ocean might sound strange, but that's only the start. Because the telescope this remotely operated submarine is heading for doesn't look up into the Mediterranean skies, but down through the planet. It's all due to the incredible properties of the neutrinos themselves.
Somewhere far out in the universe, we expect there are sources of very high-energy neutrinos. The distances are enormous. They can be millions and billions of light years away. If we're lucky, some of these neutrinos will come close to the Earth and pass through the atmosphere in Australia, pass right through the center of the Earth, through the core of the Earth, without really even noticing it's there.
Having passed through the entire planet, the neutrino will bump into an atom of seawater, causing a flash of light. The telescope, strings of light-sensitive detectors suspended in the ocean, will spot this light, or so the astronomers hope.
The name of the game of neutrino telescopes is to essentially make a neutrino sky map of the universe.
This search for the slippery cosmic neutrino represents a significant scientific challenge. Their slipperiness is what makes them so valuable. They pass through cosmic obstacles, revealing the hidden universe beyond. Observing one requires not only immense scientific and engineering prowess, but also a large helping of luck. And today, luck is in short supply. A cable connector here on the telescope on the seabed is jammed.
Normally, a broken connector isn't such a major problem. When it happens 2.5 kilometers under the sea, it's almost a disaster.
It's a long night for the team in their control room. But despite their best efforts, the connector remains jammed. Another mission will be needed. Beneath the waves, the telescope is still operational. But in over 300 years of searching, the neutrino hunters haven't found a single cosmic neutrino. Yet their enthusiasm and optimism remains undimmed.
We are convinced that these elusive neutrinos are there. We don't really know how big a detector we actually need to be able to find them. So maybe it'll happen that we won't find any. In that case, we will try to build a bigger Antares. So we have plans to build a new detector, which will be 50 times bigger than Antares.
This is the story of how great discoveries happen. Nobody really knows what the team might end up discovering.
History has shown that every time we look at the universe in a new way, we have had expectations of what we might see, but in fact the most interesting things were the things we didn't expect.
This is the true power of telescopes. Many no longer look like telescopes, but their ability to change our view of the universe places them among the most intellectually explosive instruments ever made. The 21st century renaissance in telescope construction will answer the greatest questions in cosmology and pose new ones.
It's very exciting to be an astronomer right now. We have telescopes in space, we have telescopes at mountaintops, we have telescopes in airplanes.
I certainly can't imagine a time when we would be done asking questions. I can't imagine that as human beings we'd ever be there. I know sometimes people feel insignificant or small when they think about astronomy and they think about the cosmos. And I think it's amazing that we are the people, we are the species who are able to understand how we got here. And that's not small. That's pretty amazing.